Thank you for the introduction, and thank you to the organizers for inviting us. It's clear that this topic is still on the edge, but we'll go through it and we'll see what happens. So this is work which is a collaboration between the group in physics of Maurice Skolnick and electrical engineering in Sheffield and the National EPITAXY facility. The work's been done by Aris Trapalis, a postdoc, and Charlotte Ovenden, my PhD student, who are both, well, Charlotte's already left for a spin-out company, and Aris is joining Lumentum soon, so that's why I'm here. So this perhaps is less important given the people in the room, but there was a brief introduction to quantum dots in case we had some people spilling over, followed by motivating the need for site control, and then looking at the growth experiments that we've done and some initial characterization results and conclusions. So we can skip a little bit through this, but molecular beam epitaxy, there are people here at this conference who do this, even Bozovic for one example. So effectively what we have is a vacuum system where we have individual heated sources which we evaporate onto the substrate, and we use shutters to mechanically open and close to control the material that we're growing. And generally, unless we do something very strange with the substrate, growth proceeds by one of three modes. We either have a layer by layer type approach, we have just islanding, thinking of something like water on glass, or then we have an unusual mode in the middle where we get an initial layer followed by a relaxation of the strain by forming islands, known as the Stranski-Krastanov growth. And this is the method that we're using to form quantum dots. So the important thing when we look at those films, if I just go back briefly, if I just keep growing, eventually these islands will coalesce and I'll form dislocations. I'll still produce a film. In the first case, I'll produce a nice film, and the other two I grow quite a thick distance in order to get a smooth surface. But for intermediate thicknesses, the islands formed are actually coherent. So they're a single object, they contain no defects. And that means they have very good optical properties. And if we have a large number of quantum dots, then what we see is an ensemble distribution. Remember, quantum dots, as we're told in semiconductors, a delta function like density of states. This doesn't look like a delta function. That's because they're all slightly different sizes. But what we also have is effectively standard kind of state filling, SP, shells, and so on. So we have this kind of structure where we're adding more and more electrons and holes to the dots. If we can isolate single dots, on the other hand, we end up seeing the sharp lines that we expected to see and a zoo of different states which are effectively analogous to artificial atoms. So electron hole, two electrons, two holes, or charged states. And these lines are very narrow. And what this has done is, in a standard semiconductor, we have an object which is 10 to the 4 atoms or slightly larger, where we can have a single electron and hole, and we can manipulate them. And we can create devices where we just inject electrons and holes, making lasers or LEDs, or we optically excite them to get luminescence. And we have a controllable atom, if you like, because the size, composition, strain, and the barrier materials are going to move our energies around, which means we can attack different wavelength ranges for different problems. We can watch the quantum dots forming in situ. This is the one advantage, if you like, of MBE over other techniques. We can look at electron diffraction on the surface, starting off from a kind of streaky pattern, and as we progress, we start off growing this initial layer, and then eventually when the island formation happens, you start to see an increase in the intensity at this point. And we can follow that through, and we end up with chevrons, which are showing effectively the shape of the quantum dot. And if we look in the two crystal directions, we can infer that the dots elongate. So we have this transition from streaks to spots that you'll kind of see mentioned a lot of the time. And also, if we have very good cameras, which have advanced a lot in the last 30 years, we can start thinking about real-time formation by doing sort of pulse deposition growth, so very small amounts to try and control exactly what's going on. So that's just controlling the dot growth. Now we need to control the density. So the simplest thing that we can do is just use the inherent non-uniformity that you might have in certain designs of crucible. So in this case, for a straight-walled crucible, region B doesn't see the entirety of the melt, so the deposition rate is lower here than at the edge, whereas a more conventional, more uniform crucible, region B and region A see in the same area. So we see a density gradient from the center to the edge of the wafer. That gives us a ring of the right density. We could stop rotation. And if we stop rotation, then we'll get a gradient across the wafer from the side where the source is to the opposite side. So we have a decrease in density going across, or in this case, we're showing this as emission wavelength. The emission wavelength is getting shorter. And so again, there'll be a certain region on the wafer which is good. Or we can go to extremely low growth rates. So this is dropping the growth rate down by a factor of 100 or so, meaning we grow these 2 monolayers in about 15 minutes. That gives us very low densities and very uniform. And we have this competing ripening versus nucleation. Why? So that's what quantum dots are. What are we trying to do? What we want to do is incorporate quantum dots into waveguide structures. And we want to do that so that we can move photons around on chip, effectively, eventually, to get towards on-chip quantum manipulation. Now, this is the kind of general structure. We have a sacrificial layer of material that we etch away to leave a suspended membrane with the dot layer. This is perhaps not the most exciting waveguide, but if you have a dot somewhere here and you shine a laser on it, then the light transmits along the waveguide and we scatter it out through these couplets. We could go to a slightly more complicated device. Now we have a beam splitter. If we have a quantum dot in one arm and we fire a laser in on the other, then we can start to interfere those two photons along this. We can start to make things like square root of swap, various manipulations like that, 2-photon interference. And we've demonstrated this with, say, with the quantum dot and the laser photon, where you get light coming out through the 2 ports. And 2 dots is also possible using this method. You have to hunt around and find those 2 dots and then build the structure around it. But if you want to move towards, someone's clicking on the computer. I know they're clicking, I can hear it. There we go. If we want to move towards arrays of devices, then we can't have this random positioning of the dots. We have to start putting the dots in known positions so that we can fabricate structures next to each other. We can plan where the waveguides are going to go. In this case, what we'd actually have in the end, in the idealized picture, is tunable structures. So we have N and P-type doping, put electric fields across the dot to tune the wavelength. And then you would also have tunable beam splitters in order to optimize the circuit. So if we want to make something much more complicated, we need to know where the dots are. So the approach that we're going to use seems quite simple. We're going to grow part of our wafer and then take it out and etch the surface. So we etch the surface to create some kind of nanohole. It's not necessarily triangular. This is a cartoon. Create our array of pits, put it back into the growth system, grow a bit more gallium arsenide to smooth the surface out, and then hopefully the indium arsenide will nucleate preferentially at this step because we've modified the chemical energy at that point. And then we finish off the structure and encapsulate it. There's 2 approaches that we've used so far, electron beam lithography and local anodic oxidation. So electron beam lithography is very much like photolithography. You spin a film of resist on. The difference is that you pattern this resist serially. You go along drawing all over the surface, so it does take time to create openings in the resist. And then you etch using either a wet chemical approach or a dry etching approach to create those pits. So the tuning parameters that we need for that, we have the strength of the E-beam, the dose is going to affect the kind of exposure that we get. And also the drawn size is going to affect the depth eventually that we get. So larger pits probably going to etch further when we do that. The alternative approach, good to get a student started whilst they're waiting for the MBE machine to arrive, and also good when the E-beam is down, is oxidation using an AFM tip. So in this case, in a sort of warm and humid environment, ideally controlled, but at least works well in summer, not so well in winter, you have a water bridge that forms between the tip when it's brought very close to the surface, and if you bias that, then you end up forming an oxide. And that oxide grows up and goes down into the semiconductor. So here we have an array of oxide mounds, and then we can wash those away with hydrochloric acid to leave us with an array of nanoholes. Also a serial approach, much slower than E-beam, but potentially because we don't use resist, it might give us cleaner surfaces and better results. So the general approach then is going to be, we have an E-beam pattern which consists of arrays where we have a series of different doses we're also trying to optimize, a series of different sizes of nanohole that we're going to try and make, and also a series of different spacings of those nanoholes in order to look at the competition between formation and migration across the surface. At the same time, what Charlotte did was also pattern some other regions on the wafer using LAO so that we could do the growth at the same time. And then we're going to grow our structure by MBE. So the key challenges, things we need to look for, we want good hole occupancy, i.e. we'd like to have dots in every hole. We'd ideally like them all to be the same wavelength or at least tunable. And most importantly, they need to have good optical properties. So I've already described kind of this part of the diagram, how we're going to do the etching. This is just the layer structure itself, so we have the sacrificial algas layer now in that structure. And we do a lot of ex situ cleaning, using chemical cleaning and then trying to strip off the resists with organics and so on. And then in situ we do hydrogen cleaning to remove the native oxide before transferring in the AFM that we have kind of a couple of places with dots. Now the dots may be poking slightly below and you can't see them because of the contrast, but you can then see that we're definitely getting dots in all the pits, but occasionally we're getting kind of larger objects, and then as we go even further you end up with quite big and probably dislocated dots. So we're looking at the effect of the kind of diameter on the quantum dot height. Are we actually controlling the dot growth in some way? And then also looking at, now this is single occupancy as a percentage, so anything that's empty or contains double dots doesn't count. And what we'd like this obviously is to be as high as possible. So what it tells us is that sort of at the 50 to 65 nanometer kind of hole size, we can get a good number of sites containing only one dot. How do we look at these then? So we have a number of different optical ways to look at the dots. So the first thing we've got to do is make sure that we can actually see them in our optical cryostat. So this is an optical image that's taken and we can identify at least the array, and then we can work out where a laser spot is collecting. And a quick method of doing this would be to basically sample the entire array. So if we do luminescence on the entire array, we're going to get no indication of site occupancy and so on, but we will get an indication of the kind of homogeneity of the line widths and so on, and we can move from site to site relatively quickly. The next thing we could do, which is also quick, is imaging. It requires a very expensive camera that has to go back to have its shutter replaced every once in a while. But you can then start to see luminescence from the sites, and you can start to see relative intensities. You are towards the end of the range of the camera if you're going out to 975, so things may start to seem darker than they actually are because it's a silicon detector. So this is kind of what we'd see from the first technique. We're seeing some kind of ensemble. For the second technique, we kind of see whether we're getting good occupancy and so on. So we get information on the wavelength distribution from this method and site selectivity here. So if we now compare two of the structures, this is an image from just a pure gallium arsenide sample with no buffer, and then this is from one of the waveguide structures. We can see that we're getting pretty good occupancy of the sites. In some of the arrays, we're achieving 100% occupancy in these 13 by 13 arrays. So to better understand what's going on, we've now looked at the spectral distribution of these dots. But we'll just jump and say, well, what about the LAO, which was the first thing we tried? So again, in AFM, we can see a dot sitting at the bottom. The LAO pits are quite sort of scooped and quite large because of the process. We only got to about 20% occupancy when we look in the PL map, but they are in the positions that we can draw the lines that are guides to the eye. But a lot of the dots are emitting beyond 970, so we'll need to pull those back in order to use them with silicon detectors. If we look at the EBL now, we're taking one particular set of growth parameters and just looking at the effect of the nanohole diameter. So we start off with very small nanoholes and we don't really see much. And then once we get to a size where we're actually starting to nucleate dots in the pits, we get emission at around 960. The holes get a little bit bigger, the dots seem to get a little bit bigger and the wavelength goes up. And then it comes back again when we go to the largest sizes. Now remember that what we said might happen is when the holes get too large, we can end up with multiple dots in the pits and might be pulling the distribution back. So another thing we can do, one of the extra knobs that we can tune other than the ones I've already described, is just weighting. So we deposit the indium arsenide layer and then allow things to move around on the surface and see what happens. Okay, so this is now results from a planar surface. We start off with our distribution. It's quite short wavelength. It's quite hairy. Those are the individual dots. And if we then wait for a longer and longer amount of time, going up to here 300 seconds, we allow the dots to exchange material, to possibly exchange material with the substrate as well, but we end up shifting the distribution to longer wavelength. And the kind of optimal time that we're looking for to still have dots in the range that we want is kind of 15 to 30 seconds. That's what we think is kind of a good time. If we combine that technique with extremely careful control over the amount we deposit, then we can actually end up with ultra low dot densities. So this is not an SEM image, this is photoluminescence imaging still, but this is a 50 by 50 micron image and we have 6 dots. So if we wanted to make a circuit, this is fine, but if you wanted to make lots of them, then you start to have a problem. So this is still why we want to control the position. So if we look at what happens on patterns, this was the panel we saw before where the size goes up and then appears to come back again. And if we concentrate first of all on small holes, so on small hole sizes we see kind of what we expect with the effect of the interrupt, that they move to longer wavelength, that we must be pulling more material in from the surface. And if we go to the sort of larger holes, we actually see a fairly stubborn peak that doesn't seem to want to move. And there, possibly it's getting narrower. Possibly what's happening there is this exchange of material between the dots and ending up with these 2 dots in the pit. So we can't go too large, even though we're kind of staying at the same wavelength, because 2 dots in your emitter is a problem. So if we look at those dots now in the third technique, which is to measure each dot individually, measuring its luminescence, we can actually then start to measure the line width and see, do we have sharp lines? Do we have exciton by exciton and so on? And they do show good optical properties. So again, shoving things at the bottom of the slide, a distribution of line widths that we've measured for E-beam for effectively a small number of arrays. So we have a modal line width that's around 40, but our best line width is approaching our resolution limit of our spectrometer, which is about 20 microeV. So it's possible that if you look at enough arrays, you might find dots which are even narrower line width than that. If we look at the LAO, LAO doesn't let you draw as many pits. The statistics are clearly worse. The best line width is not that far away, which is substantially better than most other reports of LAO in the literature, where they've had to use 2 layers of dots. But the mode is sort of at 60. So this is promising. It shows that, remembering that we have a growth interface, which is 30 nanometers away from the dot layer, that we're still getting very good optical properties from these, and we want to push them further, and there's various different ways that we could do that. So, said it was short. In conclusion, for a variety of conditions, we can control the position of the quantum dots. We can tune the wavelength. We've recently done experiments where we chop the tops off the dots to bring them back, but we haven't sort of got that all sorted out yet to present. But we're in the right range for silicon detectors, for free space quantum optics, from mountaintop to mountaintop, or short distance fiber. We have dots, and we can do this by tuning the nanohole size and the growth interrupt. I've described 2 serial techniques for patterning. Okay, they're not necessarily scalable over the long time. There are ways of doing E-beam where you don't turn the beam off. If you have the right size, you could just draw the whole wafer and just dwell and stop, which would speed up the process compared to blanking and trying to fill in the holes. But the results indicate that they're suitable for use in devices. So the next step that we have is to incorporate them into an active structure. So in this case, the top and bottom of the waveguide, we put P and N-type doping to make a diode so that we can inject that current I talked about at the beginning. And if we have a quantum dot over on this side, if we isolate the top by cutting into the P-type layer so that there's no conduction between the two, we then have an emitter which can launch into the fiber, into the waveguide, and then scatter out through the top. So again, a simple initial experiment followed by emission into more complicated structures. So with that, I'll conclude. If you want to visit the lab, you can do so by going on a virtual tour. And this is the machine where everything is grown on. So, thank you.
Thank you very much for a very clear and interesting talk. Questions? Maybe I should start a discussion myself. You showed some inhomogeneous broadening in these ordered systems. Is the inhomogeneous broadening comparable to what you have on non-structured surfaces? Or is it better? Because now you have a feeding, maybe that is more controlled.
In some, so for the people who are using this patterning to control the density for kind of laser devices, they've shown that they can narrow the distribution compared to the inhomogeneous width. So they can reduce it to like 13 MeV where they're getting 15 on the flat surface. In our case, we probably don't have enough sites to build up good statistics, but it looks broader at the moment. And then there's a question of whether you've got variations going across your E-beam pattern that you haven't compensated for, or whether, it's a long way back, I'll not scroll, your patterning parameters are such that your initial holes are uniform. That's one thing which is kind of, from a manufacturability standpoint, looking at the patterning, trying to determine the size distribution of the holes, including the depth. The depth with dry etching is not perfect across a whole wafer. And then seeing whether that translates to controlling is kind of a next step. But yeah, right now it looks worse. They're quite broad distributions when we were looking in just ensemble.
Other questions?
Ian, do you see, how big is your buffer layer? How much gallium arsenide did you put underneath?
30.
Did you try different values? Is there?
That was what we ended up with as being reasonable, having just done some planar tests very early on. We should go back and repeat the planar testing. But we could, of course, just put a dot right at the bottom of the pit, which then will be not optically active to allow us to strain couple to go further away. But you have a limit in the waveguide of the geometry of how deep you could etch your pit. Then you could grow more by flattening off and going too high in the waveguide. So there's kind of, I think 20 nanometers up and down inside the waveguide is okay for positioning that dot.
Another question is, you mentioned, there are obviously some new properties during growth on the wafer scale. Did you grow your position dot on quarters or full wafers?
Quarters.
Do you see any non-uniformities across those quarters? For example, maybe you've got sides on the wafers which exhibit, let's say, 90% of photonic occupancy, and somewhere further away you would have different statistics.
So in that sense, we have a reasonable number of patterns on the wafer, but we haven't looked as extensively. And kind of the weirdest things we've seen, if you like, are differences even with just a single array about whether you do or don't have an array next to it. So you get quite high occupancy near some of the alignment marks, and if they're too close, you're sucking the dots away. So we saw some patterns where you might be missing one of them, and then everything looks different. So you really have to think about the stuff you're putting around the array. It needs to be close enough to be able to align to make these structures, but if it's too close, it's actually sucking up too much of the indium. Across, so it's a quarter of a 3-inch wafer, so it's pretty large. We haven't started to look across all of the patterns to see whether there's kind of edge effects and so on going on. We're not at a temperature that's so hot that we could be desorbing at the edges of the wafers. We kind of check that, but there still could be some variation in the migration length.
Any other questions from the audience? And the last question
Okay.
for you, I was intrigued by the remark that you made about the read measurements, and that you actually can see the dot anisotropy in that. Did you link this really with AFM measurements or with other measurements?
People have, so that, I mean, that wasn't my read image, that's from Springfield, but yeah, I mean, you can see that, you know the crystal directions it's going in, you can measure facet angles and so on in the read. It does require, to start to see the facet angles, a reasonably high density. When you're looking at the kind of trying to grow these very low density dots, it's more, I can just see the first spot appearing, if you like. It's probably too far back. So actually to see the change in the facet angle, and actually the other thing you can see is when the third line appears, that gives you an indication that you have a lot of dots. But in terms of where we want to be for measuring, it's between here and here, which on any projector screen is, there's no change. But that's compared to what it used to be, which is your head like a photographer looking at just the fluorescent screen yourself and staring and convincing yourself it's happened. So the other thing I've kind of had project students looking at is trying to look at kind of machine learning approaches to try and identify when this might be happening. So principal component analysis and so on to try and work it out. Because even though MBE is not self-driving cars, there's still scope for autonomy of either recognizing the correct pattern for doing things. So
If you can feedback directly in
Yeah.
the roles, during the roles. Perfect.
Yeah.
Let's thank Ian.
Thank you.